Hi guys, in this video we are going to introduce the concept of Hess's law as our second approach to finding delta H of reactions. Now, as you can see from the little image down here, Hess's law really just boils down to an application of the fact that delta H is an state function. Okay? In other words, changes in enthalpy of any sort of system do not depend on the path. So basically, you can come up with any sort of path that's convenient that gets you from point A to point B, take the difference between the two of them, and you will be able to find the corresponding delta H. So to build this up, let's explore some ground rules for working with thermochemical equations. So remember that we saw on the outset of enthalpy discussion was that this idea that constructing the thermochemical equation and the corresponding delta H of reaction, all right, they are intimately tied to one another, okay? Which means if you have a given thermochemical equation and you change the reaction in some way, then there's going to be a prescribed change in the associated delta H. And there's three major rules that we want to keep in mind. So the first one is rather intuitive. Let's suppose I have a given chemical reaction, A plus 2B going to C, and there is a corresponding delta H of reaction, delta H1. If we multiply this chemical reaction equation by 2, multiplying every one of those stoichiometric coefficients by 2, then the corresponding delta H of reaction, and denoted delta H sub 2, is simply going to be 2 times the delta H of that initial thermochemical reaction, right? So you multiply the coefficients by a number, you need to multiply the corresponding delta H as well, right? So in the same sort of vein, if we were to, say, switch the direction of the reaction, rather than going uphill, we go downhill, or vice versa, then the magnitude of that chemical reaction, the delta H of that chemical reaction is going to remain the same. All that will change is the sign. So for example, if we have an A and 2B up here, right, and our little delta H of reaction, and we go down here to form some product C, right, then we're going to have a delta H1, right, that will be negative. We're obviously giving off energy here, but if we switch the process around to go back up, it's the same magnitude, but it will be an opposite sign. Right? Now, the last relationship that we want to keep in mind comes back to how do we deal with chemical reaction equations when we're adding them together. Well, we've done this before. If we had, for example, one chemical reaction, A plus 2B going to C, and then I have another chemical reaction that takes C to a new product, D in this case, and I add those chemical reaction equations together, we cancel off the terms that show up on the left and right. So there's one C on the right, one C on the left. So what's left is just the reactants A and 2B and the products 2D, right? So we can add together chemical reaction equations just like before. Well, it turns out that if you do this, you need to add the corresponding enthalpies to get the overall enthalpy of reaction for this combined process. Okay, so it's really this third step then that lays the foundation for what we call Hess's law. So basically, Hess's law states that the change in enthalpy for any stepwise process is going to be the sum of the enthalpies for each of those steps, right? And again, this is a direct consequence of enthalpy being a state function. Okay, it's only depending on the initial and final states, so we just add them all together and we're home free. So to illustrate this previous example, we could switch it around and say, okay, well, let's say we start off with some lower enthalpy reactants, A and 2B. They form products, C, but then that product C forms a new product and a second chemical reaction here that goes to an even lower enthalpy than those initial starting material. And our goal then is to figure out this delta H3 in purple, right? The magnitude of this purple arrow. Well, to do that, all we need to do is add together how much we go up and how much we drop down, okay? And so if you add the blue up, the red down, then you will arrive at this delta H3. So the way that these Hess's law problems are typically formed is, you start off with some unknown chemical reaction equation, right, for which there's going to be some delta H of reaction, but you don't know what it is, right? But then you are given a set of known chemical reaction equations with their corresponding delta H's. And so then the task comes down to figuring out a way to use our three rules that we talked about previously to modify, move around, flip-flop, and add together this set of three given chemical reaction equations to somehow arrive at our desired overall reaction. So we'll just kind of jump through the solution on this one, and we'll work through in more detail in the next one just to see what I'm talking about here. So we need to somehow reproduce this overall chemical reaction equation. Okay? So we have to go through each one of these chemical reaction equations in turn and basically see how can we modify this so that it can contribute to the formation of our desired chemical reaction. We can see our first given equation here, this combustion of propane, has propane as a reactant, but we want propane as a product. So what we're going to do is flip this equation number one here. So we're going to flip equation number one and write it down here, and then we're going to change the corresponding sign of the delta H according to rule 2. Right? So now we have our propane as a product. Okay? Then we're going to come to our next chemical reaction equation, and we're going to see that we want to have 3 moles of solid carbon. Okay? So this chemical reaction equation does, of course, have carbon solid as a reactant. However, there's only 1 molar equivalent. So we need to somehow get it up to 3 molar equivalents. Well, we're going to do that by multiplying every term in that equation number 2 here by 3. And so, of course, if we multiply every coefficient in the chemical reaction equation by 3, the thermochemical reaction equation, correctly represented, must have a delta H that is also multiplied by 3. So we're going to multiply this by 3, bring it down there. All right, and that's rule number 1 up there on the previous slides. And then finally, we're going to get our other reactant, H2, by looking at the third chemical reaction equation. We need 4 moles of H2. This given reaction has 2 moles of H2, so we're going to multiply everything by 2 to arrive at our last contribution to the enthalpy. And so what we're doing here is we've now constructed 3 different chemical reaction equations, based on the desired products and reactants. And then we can go back through and see and to double check to make sure that all the other reactants and products are in fact going to cancel out. So we can see we have 3 moles of CO2 on the left-hand side. Well, that's going to directly cancel with the 3 moles of CO2 on the right-hand side. Similarly, H2O, 4 moles of H2O is going to cancel out. The 5O2 is going to cancel out with the 3 and 2 moles of H2O on the left-hand reactant side for the second and third chemical reaction equations. And then, carrying over the surviving terms, right, we have our desired chemical reaction equation and the corresponding delta H obtained by summing up these delta H's for each one of the steps. So just to make sure we understand the process here, let's work through one more example together. So in this example, we're given, once again, an unknown, a chemical reaction with an unknown delta H, and our job will be to find that delta H of reaction, and we are given a set of known chemical reactions that we are going to use to construct a series of reactions that gets us from this initial state to this final state. So what I like to do is to start by building up that initial state. And of course, there's any number of ways you could go about solving this problem. I just like to start here with our our initial starting material and then build towards a the products that we want. So we can see we want N2O gas as a reactant. Okay, so we can then scan through all of our given chemical reactions to figure out where N2O gas shows up, and it shows up right here. And it's a reactant already. So what we're going to do is take chemical reaction number 3 here and divide it by 2 to get the desired stoichiometric coefficient, and go ahead and write it down. And so I'm going to make sure to include that, divided by 2 on that delta H here, all right, to take into account that I'm only taking half of this reaction. Okay, so I've got my first reactant. Now I'm going to come over here and look at my second reactant, NO2 gas. So I'm going to do the same thing, come through and look for which one of these chemical reaction equations has NO2 gas, and of course it's going to be this guy. However, in our first equation here, NO2 gas is showing up as a product. So what we need to do is flip it to put NO2 as a reactant, and we're going to need to divide by 2 to make sure that we only have 1 mole of NO2 gas. So I'm going to flip the sign and divide all of these terms by 2. Okay? And as a result, the corresponding delta H is not only going to have the opposite sign, so it's going to be plus 113.1 kilojoules, but it's also divided by 2. Okay? And then lastly, we're going to use our final chemical reaction equation we haven't used yet to figure out how much, or to form our product of NO gas. And in this second chemical reaction equation that we're given, we are forming NO gas as a product, but of course we're forming 2 moles, as you can see from that stoichiometric coefficient, where we need 3 moles. So now we're going to take this reaction as written. However, we're in the direction it's written. However, we're going to have to multiply by 3 halves. So we're going to have to take 3 halves N2 gas plus 3 halves O2 gas, right, to form 3 NO gas. And then our delta H is going to be 3 halves times 182.6 kilojoules. Okay. Then we can see if we add up all of these terms, we have a 1/2. Okay, and now we're ready to start canceling these out. But now notice, if we start trying to cancel out the terms that show up on the left and right hand side of the reaction arrow, something interesting pops up. We notice that this second reaction is actually giving us 1 equivalent of NO gas. Okay? And at the end of the day, remember, we want 3 equivalents of NO gas, and we adjusted that second chemical reaction equation to give us 3, but we already had 1. So in reality, we only needed 2. So we can keep that chemical reaction equation as written, with just coefficients of 1 in front of each one of these guys, and then we'll find that the corresponding delta E, again, of course, doesn't need, or delta H doesn't need to be adjusted. Then we can find that the 1/2 O2 and 1/2 O2 will come together to cancel out the 1 O2 on the left-hand side. And similarly with the N2, cancel out the N2, add both of these reactions together, and we will have N2O gas, this guy, plus NO2 gas, this guy, forming a total of 3 moles of NO gas, and our corresponding delta H of reaction. Now, this is a good point to bring up, that if you are working through this problem using different tables, different values for delta H of reactions for these different terms here, you may find some discrepancies. Okay, so these taken from a textbook value, you could look online, find slightly different values for those delta H of reactions. And it turns out that there are some challenges associated with coming up with a delta H. And we'll talk about that later on, but just sort of file that away. You could easily be getting different delta H values. They could differ by as many as a few kilojoules per mole sometimes. But for any homework or exam problem, I will give you the values of delta H set up, tabulated in this form, and you'll basically just use these guys and trust them. All right, so then that concludes our discussion of Hess's law, how to calculate delta H using Hess's law, and we've already seen how to calculate delta H using calorimetry. In our final video then, we are going to talk about the concept of standard enthalpies of formation and how to use those guys to calculate delta H for a given reaction.